Hey guys, this one we're going to have a piston cylinder assembly, again, of a gas, and it's going to consist of three processes. First one, we've got constant pressure, and then we've got pressure given as 1.4 bar, we've got volume given as 0.028 cubic meters, then we've got our work, which is a positive 10.5 kilojoules. Now the second process, we have compression with this relationship, so pressure times volume is constant, and then U3 equals U2. Finally, we've got process 3.1, where we have constant volume. Change in internal energy is negative 26.4. And then we're going to ignore these two effects like we have been doing. First, we're going to sketch this on a diagram. Then we'll find network for the cycle, and then we'll calculate heat transfer for just process 1-2. Let's go ahead and start with drawing this on the diagram. So there's V, there's P. Now we know the pressure and the volume at 1. So let's put those values on here. We got 1.4 and then our volume is 0.028. So there's state 1. Now state 2, if you look between here and here, we don't have anything about volume. That's state 2. We do know constant pressure though. Happens between 1 and 2. So I'm just going to put a V2 here and put a dot at a pressure of 1.4. So we know we're going to have a horizontal line there. Now going from 2 to 3, all we know is we have this relationship, and that's basically all we got there. And then if we look down in process 3.1, let's see if we find anything for state 3 that we could use. Here we know we have constant volume. So if we're going to have constant volume going between 3 and 1, what does that tell us about the volume? It tells us it's going to be the same as state 1. Now notice I put it up here, and I put it up here because remember process 2.3 is compression. So if you're compressing the gas, you're reducing the volume, which in turn increases the pressure. So we're going to go like that, and then finally we go down to 1. So that'll be your diagram. Now in part B, we want to find the net work. The net work, remember, is just where you go along and find the work for all three processes and then sum those up. So we get W12 plus W23 plus W31. Now if you look at these, W12, that was given, right? That was positive 10.5 kilojoules. W23, we don't know that. That wasn't given. And then W31, what do we have for that? That's right, that should be 0 because we have constant volume. Remember, anytime on these diagrams you have a straight vertical line, you're not going to have work done because volume's not changing. So that one goes away. So let's put, because V is constant. That leaves us with this one. We got to find W23. For this, we've got this relationship that we can use, and obviously we've got volume change, so we're going to have work. So let's write out that relationship there. Pressure times volume is a constant. Let's use this to get our equation for pressure that we need in the integral. So it's going to be C over V. And now let's write out the integral. Alright, so work from 2.3 is going to go from V2 to V3, and we're going to have C over V times dV. Now when you integrate that, you're going to get C times the natural log of volume, and you're going to evaluate at V2 and V3. Plug these limits in, and let's look at C. What's C going to be? It's just pressure times volume. So let's put PV times the natural log V3 over V2. Alright, now we don't know V2 and we do know V3 though. Okay, so V2 we're going to leave as an unknown right now, but V3, that's the same as V1, right? So we know that. So let's replace V3 here with V1. So a PV times natural log of V1 over V2. Call that equation 1. Now let's go ahead and get V2. We can find this C constant in just a second. So let's find V2 first though. For V2, we're going to look at process 1, 2, and let's look at this work. Work was given to us. So we know work is 10.5, and that's got to equal the integral of the pressure, which was 1.4, times the change in the volume. Okay, so now if we go ahead and write all this out, we're going to have 10.5 kilojoules. That's going to equal the pressure, 1.4 bar, times V2 minus the 0.028 cubic meters. And that's from the V3 term. Okay, or V1 in this case. So we're doing V2 minus V1. All right, that might make it easier to see. So those are our limits. Now we've got this. So our unknown here is V2, so we can use this to solve for V2. So V2 is going to be 0.103 cubic meters. Now we'll take this, use it in equation 1. Alright, so for P, let's go ahead and use the pressure that we had, which was 1.4 bar. Now I want to convert that over from bar. I want that to be in kilojoules. So this is P1. So for kilojoules, you're going to have 140 kilojoules. And you get that by using that 10 to the 5th Newton per meter squared per bar times the 1 kilojoule per 10 to the 3 Newton meters. Those conversions will get you to kilojoules. All right, so now we've got that, and then what we want to do, and actually I forgot to mention that you have to convert these here too, because we have kilojoules and then you have bar. I kind of skipped that step. But if you convert this one over to bar, then the bars will cancel. And let's see. All right, so now we have that. Make sure you do that step, otherwise you're not going to get this value. So now that we have that, we're going to have 150 kilojoules or 140 kilojoules for P1. All right, so that's P1, and we're going to use that in equation 1. Guys, I keep writing the wrong thing here. All right, so we got 140, and then you're going to put the volume that we've got. So let's put 0.103 cubic meters. That's what we have for V2. And now we're going to have the natural log, and we got V1 over V2. V1 is going to be 0.028 cubic meters. Put that over 0.103 cubic meters. And that'll give you negative 18.78 kilojoules. All right, so this is going to be your work for process 1, 2. Actually, that's not work. That's for process 2, 3. Sorry, guys. Okay, so now we got work for process 2, 3. Now let's take it and we're going to plug it back up into here. Hopefully I won't write anything else incorrectly. Okay, so the work of our cycle then is going to be 10.5, because that was the work for 1, 2. That's in kilojoules, and then we have the minus 18.78 kilojoules from right there. And then work for 3, 1, that went to 0, remember. So now you just sum these up. So your net work is going to be negative 8.28 kilojoules. All right, so it's negative, so energy due to work is being transferred into the system or work's being done on the system. Now for Q, for part C, we're just going to use our energy balance equation. So remember, that's delta KE plus delta PE plus delta U equals Q minus W. And we basically have what we need here to solve this. Now, let's see. This goes away, that goes away. So delta U, we want this for process 1, 2. So we're going to have U2 minus U1 equals Q 1, 2 minus W1, 2. All right. So now we've got that. Now you got to look at these U values. We know from up here at the top that U3 is equal to U2, and then we've got this difference here it's given to us. So if U2 is equal to U3, then that means U2 minus U1 is going to be negative 26.4 kilojoules. All right. So now you'll have that relationship. So basically you just took that difference for the internal energies for process 3.1 and just switched it out, because before it had U3 in it, so just switch it and then write it in the order that we need. Now we can take this, plug it in over here, so we get 26.4 kilojoules. That's going to equal Q12 minus the 10.5 kilojoules. So then finally you get your Q, which is 36.9 kilojoules. Alright, so that's how you go about getting Q. Alright. Okay guys, so that's it. The only thing I didn't write down here were these unit conversions. I should have written those down, but I wouldn't have had room anyway, so make sure you do those though. Otherwise you're not going to get the same answers.